In this package, we're going to discuss a few worked out examples from the textbook Castellan. And specifically on this slide, we will look at the worked out example under section 2.2, molar mass of a gas, Avogadro's hypothesis, and the ideal gas law. So the problem worked out here in the book is a gas is contained in 50 liters under 8 atmosphere pressure at 20 degrees centigrade. How many moles of the gas are in the container? This is, of course, a very low level problem, but I will take this opportunity to illustrate how to work through the units. And just to remind you, and I'm sure you have done this many times before, but some of you may have done it a while ago. So it's good to remind ourselves how we handle the units and how to pick an equation, how to pick a strategy to solve the problem. Just to start off this week, we will convert the units into SI units in the beginning to illustrate and familiarize ourselves with the SI units. The next week, Module 2, worked out examples, I will show you a shortcut to deal with the units. So for now, we'll change the units into SI units. For example, the temperature of the gas is given as 20 degrees centigrade. And we want to use the ideal gas law, which is implicit here, that the gas is ideal. You need to assume that to solve this problem. Then we know that we cannot use centigrade scale directly, but if we were to convert that into the Kelvin scale, then we can substitute the numbers into the equation PV equals to nRT. So temperature T capital is in Kelvin scale is equal to 273.15 plus 20 degrees centigrade. That's our conversion factor. So it gives us 293K, which is bolded to illustrate the new number. The volume is given in 50 liters, and we need to convert that into standard units of cubic meters, which I've done here. And similarly, the pressure is given in atmospheres, 8 atmospheres. So we convert them into pascals by multiplying with 1.013 times 10 to the 5 pascals per atmosphere. So now we work the units up into the SI. Now let's apply the equation 2.13 into this problem. PV equals to nRT. And so now N will be equal to, which is what is asked, the number of moles equals to PV over RT. And so that is 8 times 1.013 times 10 to the 5 pascals, 0.050 cubic meters in the numerator, and then R value and temperature. I'm recording for a few minutes, okay? So now adding the multiplying the items together and adjusting the units, should be able to get the number of moles equal to 16.6 moles. In the above substitution, something is missing. I would like you to figure that out. Periodically we try to do this so that you're paying close attention to what we're doing. In this second slide, we're going to look at example 2.3, section 2.9. The partial pressure of argon in the atmosphere is given, 0.0093 atmospheres. what is the pressure of argon at a height of 50 kilometers at 20 degrees centigrade. Acceleration due to gravity g is given to us. So first we convert into SI units. I have shown that here. Then we use equation 2.39, which is the barometric law. P equals to P0 e to the power minus m molar mass, g acceleration due to gravity, z the height of the gas column divided by r and temperature T. So it's in this sort of situations be easier to first calculate the exponent and then substitute into the equation. The exponent we have is mg z over RT. So making those substitutions, you see those units and figure out how to cancel them, and in the end you should get 8.03. The question now to you guys is, what are the units of this mg z over RT? Are there any units, or is this dimensionless? Think about that before you answer. Then we can now substitute the value into the main equation. P equals to P0 e to the power minus mgz over RT, and then you get the answer from it. So solving problems need not to be hard, need not to be difficult. And of course, the book has chosen very, very simple problems to work out. So initially, this is what we will do anyway. We take simple problems to work out and then slowly increase the difficulty or the degree of difficulty of the problems as we proceed. So the next example is 4.1. Using equations 4.16 and 4.17, we can write these two. What are these? First, look at on the right side. The speed root mean square of an ideal gas is equal to square root of 3RT over m. M is the molar mass. So if we take two gas samples and compare their RMS speeds, we get CRMS1 divided by CRMS2, then is equal to square root of m2 over m1. Notice that the gas velocity c1 is on the numerator, c2 is on the denominator, and under the square root, mass m2 is in the numerator and m1 is in the denominator. This is because the equation on the right hand side shows that mass and the speed are inversely related to each other, the square root function in them. So then that's equal to square root of m2 or m1. Simply replace the masses by atomic molecular masses. So in this case, we compare the CRMS of hydrogen with that of oxygen. We can write the following expression. CRMS of H2 equals to CRMS of oxygen multiplied by square root of 32 over 2. 32 over 2 is 16, and square root of 16 is 4. So we can say that the root mean square speed of hydrogen is about 4 times that of oxygen. So this is not come as a surprise, but clearly illustrates that the hydrogen molecules moving much faster than that of the oxygen molecules. This is simply because of the differences in their masses. And we can be more exact and say that the hydrogen molecules traveling 4 times faster than oxygen under any temperature pressure conditions. And so, but the average kinetic energy of the two molecules are the same. And that's the interesting part as well. So I would like you to figure this out. What are the kinetic energies of the O2 and H2 molecules? Are they really equal? The next example 4.3, it only simply illustrates how to use the distribution functions. And so the distribution function towards the end of this module you would learn is a g average, that is your function, equals to integral c0 to c infinity gc dnc over n. So by the time you reviewed the corresponding lecture material, all this would make sense to you by that point. Simply saying that if you were to sum the property from 0 to infinity for all the molecules and then divide with n, you get the average. See, that is very simple. So if I take the velocities of molecule 1, 2, 3, 4, 5 and sum them all up and divide by the number of molecules, I have the average velocity. That's exactly what this is all about. So take 4.57, we apply it. So let's say we want to use average energy. Average energy is half mc squared. So that is epsilon half mc squared. M is the mass, c is the velocity. So now we can substitute this in equation 4.57. Then we get integral 0 to infinity 1/2 mc squared dnc over n. So now if we substitute the value of dnc and integrate, you should get E equals to 3/2 kT. Average energy of one molecule is 3/2 kT. So this is the illustration of how we can calculate the average properties of molecules by knowing the distribution functions. And we use this in the deduction of beta in the distribution function in the lecture, and you will see this already by that point.